Mexico, and he dropped me an email, and I said, you have to come here to give a seminar and to know my colleagues, right? So let me be very brief about Marc. So Marc Messard has held CNRS positions at École Normale Supérieure at the University de Paris Sur, and he was the director of the École Normale for 10 years, from 2012 until 2022. He's presently a professor at Bocconi University, and he has received many, many prizes that I'm not going to enumerate. For instance, the most important one is the Larson Sager Prize, or maybe that's the most important one. I have no idea, because you have many, many prizes, okay? So Marc is very well known for working and doing seminal work in statistical physics. So these are the physical systems, spin glasses, structural glasses, random manifolds, polymers, and applications to biology, economics, finance, information theory, computer science, statistics, etc., etc., etc. So today he's going to talk about the connection, very interesting connection between spin glasses and machine learning. So thank you very much.
Thank you. Thanks a lot, Isaac, for this invitation, for this nice introduction. Thank you, everyone, for being here. I'm sorry I cannot speak in Spanish. I could have given the talk in Italian. That would be an approximation, but I think at this point it's probably easier to switch to English. So yes, I wanted to give a talk a bit taking a kind of high-level point of view on what has been the evolution of the theory of statistical physics of disordered systems since its creation. So I wanted to step back in some sense. I will separate the talk in three different sections. One is a kind of historical summary of what happens in spin glasses and why it has been a revolution for statistical physics, why it has opened a lot of other fields. I want to introduce to machine learning and the connection with machine learning and large dimensional inference. And I want to tell about the new direction, which I find very, very interesting, which is a question of data structure in machine learning, which asks new challenges to spin glass theory. So let's take a very long-term perspective. 150 years ago is more or less when statistical physics was created. As everyone knows, it was a big step in the sense that one has to give up the deterministic description of a system and instead adopt a probabilistic approach. So one gives up the idea of following each particle, but then one wants to understand the probability distribution of their position or their momenta, etc. 50 years ago, so that's 1/3 of the lifetime of statistical physics, there was a creation, a bit caricatural, I mean, there are not sharp dates, but more or less. 50 years ago, there is a creation of a new branch of statistical physics, strongly disordered systems, that pose very formidable challenges. And one very important benchmark in this creation was the theory of spin glasses, which gave rise to major development in the last 4 decades, starting with Paris's replica solution of the SK model in 1979, and which, as is known, also gave rise to his Nobel Prize 2 years ago. So I will summarize, I want to try to summarize why this spin glass theory has been an important guideline for the development of statistical physics. And I want to explain you why there were 4 big challenges that had to be met in order to develop a theory of spin glasses. And so the first challenge is a question that I call the ensemble of samples. I will try to explain it. A spin glass is a disordered magnetic material. The archetype could be copper manganese. You have impurities of manganese in copper. The impurities of manganese, they have a magnetic moment, they have spins, and they interact. And they actually interact via the electron of the copper. And this creates indirect interaction, which are relatively long range. But the most important part of this interaction is that if you look at 2 spins, I and J, let me try to take the pointer here. If you take 2 spins I and J, they will have a pair interaction. So the energy will depend on the spins like minus Jij, Sisj, that's the usual exchange coupling. But you remember from the basics of statistical physics is that there are two types of materials. There are materials in which Jij is positive, and so you minimize the energy by aligning the spins. And there are the Jij which are negative, and then you have anti-ferromagnetic interaction. And here in spin glasses, what you have is a Jij which depends on the distance between the impurities. And so because of that, for some pairs it is ferromagnetic, other pairs it is anti-ferromagnetic, and that's a complicated system. It's so complicated that in principle what you have to solve is you have to understand what is a Boltzmann distribution, what is the probability of a configuration of spins. This is e to the minus beta times this energy which is here. And so what I would like to understand is what is this probability distribution for a given set of coupling, which means a given set of positions. The position, the impurities, they do not diffuse, they are locked. And so if I have prepared a sample of copper manganese, I have my random positions of the manganese, and in principle I have the Jij, and in principle my problem is well defined. I should be able to tell you what are the possible configurations of the spins. But you see here that a priori there is one probability measure to be studied for each sample. Because if I change the sample, I change the position of impurities, I change the J, I change the probability distribution. And so this is a nightmare because it means that a priori I have a new physical problem each time I draw a new sample. And so this was the first challenge to be met. And the first challenge was to really define an ensemble of samples, which is a probability distribution on the set of couplings. So it would mean maybe I can model very well the position of the impurities. And so I generate a random position of impurities with that model. This will give me a probability of the J. And so really what it boils up to is you have first to generate a sample with a certain probability. And remember that the J, they are over the n variable. It's a very large number. It's an Avogadro number of parameters that define my probability distribution here. So there is no way that I will give you the list of the J for a sample of copper manganese. No way. You cannot write it on a computer or on anything. But the thing that you can approximate is what is the probability distribution of these. And so the problem translates into a second level of probability. You have a first level of probabilities in which you generate a sample, and then give the J, and then given the sample, what is the probability distribution of the spin. So this was a first major step, and there is two sources of disorder. There is a quench disorder. The quench disorder is like the position of the impurities. Each sample is different from all the other ones. And then there is thermal disorder. Given a sample, the spins fluctuate. So you have two levels of probability. And then, of course, so technically, for instance, maybe in some models, you will take the Jij to be independent random normal Gaussian random variable. But then what was found is that, fortunately, there are quite a few properties which actually do not depend on the sample. For instance, if you look at the total magnetization, you put the system in a magnetic field and you measure the magnetization. This does not depend on the sample. You create a 1% manganese in copper here, or you create another sample in Grenoble or one in Roma. You do the measurement, you find the same. So it means that there are properties which are what we call self-averaging. They are very important. The magnetization, the internal energy, the specific heat, all the thermodynamic measurement, they are independent of the sample in the end. They are the same for almost all samples. So on the other hand, there are sample-dependent details, like what is the ground state, what is the configuration of spins that minimize the energy. This depends on the J, so it depends on the sample. The second challenge is in homogeneity. Every spin is in a different environment. So there are different magnetizations. It means that the system, when you cool it to 0 temperature, there are some spins which point up, others which point down. All this is a big mess. It's very disordered. And it's very hard to understand what will be the configuration that the system can take. There was a nice breakthrough for that long ago already by Fowles, Anderson, and Palmer in 1976. they wrote a system of mean-field coupled equations, which are n-coupled equations for the local magnetization. You have n local magnetization, and so if you succeed in writing this equation, it's already still complicated because you have coupled equations to solve, but it's already it's a major simplification with respect to the starting point that I had in the previous slide. That was a probability distribution over an exponentially large number of configurations. So that is the second ingredient in homogeneity. And it turned out that the way to develop the theory was to look at the statistical description of the magnetizations, which are the local fields. And this is called the cavity method. And so the third challenge is the rough landscape. If you look at a ferromagnet, basically at low temperature, at low enough temperature, below the Curie temperature, you have two states where the spins align, in majority align up or in majority align down. There is symmetry breaking, spontaneous breaking, symmetry. In a spin glass, you have many possible states, all with the same energy, and they are disordered. There is no obvious symmetry that is broken, so you cannot, if you have found this one, you cannot easily find it. And on top of that, you have a lot of metastable states. So this is what we call the rough landscape. It turned into something which was very interesting, a connection of the landscape. This is a landscape in large dimension. So my figure here is totally misleading. You should not rely on this figure. You have to understand that I am drawing a space which is n dimension with n very large. But nevertheless, I can draw only two-dimensional drawing on my laptop. And so the thing that was very interesting is that it created a very fruitful contact with optimization, because it's a very hard optimization problem. I give you a Hamiltonian, an energy function of a spin glass. I give you, let's say, for 10,000 spins, I give you a matrix 10,000 by 10,000, which give you the interaction between the pairs of spins. And I ask you, what is the ground state? What is the configuration of S that minimizes the energy? This turns out to be what is called the NP-hard problem. So it's a problem that, in the worst case, you will need an exponential time in order to solve it. Exponential in the size of the system. So it's a very important problem from the point of view of computer science. And it's also an interesting problem from the point of view of physics, and it created a lot of useful development. The fourth challenge is really non-equilibrium, because the proliferation of metastable states, it slows down the dynamics. Even in a real spin glass, let's say, in which the typical spin flip time would be maybe 10 to the minus 15 seconds, and you do experiments on hours, even on that time scale, you do not reach equilibrium. The system is out of equilibrium. It's actually aging. The spin glass system, which you have prepared, you have prepared it at low temperature today, and you do the experiment now, or you do the experiment in 15 days, it will have a slightly different response function to a perturbation. If you turn the magnetic field now and you measure the magnetization, you will find a result. If you turn the magnetic field in 15 days and measure the magnetization, you'll find a different result. It says that the system ages. It's a property that is very typical of glassy systems. I mean, even plastic glasses. I mean, a plastic ruler. This is not a ruler, but it's a plastic thing. Imagine that I would measure the length of this thing, and I compress it. And I look at the reaction, or I look at the response function. What is the length as function of the force that I am applying? Okay? You can plot that. If I do that to a plastic ruler that has been prepared 2 days ago, I will find a certain response function. My plastic ruler has been prepared 2 years ago, I will find a slightly different response. Plastic is aging, and it's measured in the response property. The same thing in glasses. And this is due to this very shape here. So this is some example of experiments of explaining that one does not reach equilibrium. That's what you find as magnetization, applying a small magnetic field in the linear response regime. And you see that if you are at high temperature, there is a single response. You find a certain magnetic susceptibility. And if you go at low temperature, there are two curves. One is a curve in which you have applied the magnetic field and then you cool the system, and then you remain at that. And the other curve is you cool the system at 0 magnetic field, you apply the magnetic field, you measure the magnetization. They should be the same if the system were that field. So this gap tells you how far you are from equilibrium. And it was one of the major results of the Parisi solution of the mean field theory to show that in the mean field theory, you have these two curves. You have really this difference between a linear response reaction, which is the zero field cooled susceptibility, and the equilibrium one, which would be the field cooled. So this is a new branch of statistical physics, studies ensembles of problems. There is disorder, each spin sees a different local field, so they freeze in random direction. There is a rough landscape and strong out of equilibrium dynamical effect. So this opened the possibility of studying that even is mind-boggling, if you think. And it opened the possibility to use this same kind of idea in all kinds of systems in which you have atoms, in the Greek sense of the term, that is elementary constituents which interact in a disordered way. For instance, agents. If you have interacting agents that do things on the market, you have an organized market, financial market, you have agents, each one has its strategy. If all agents have the same strategy, then you can work out a theory of the representative agent. That is, you do what we do, the mean field theory that the physicists do, you do that with the representative agent. Just need to solve what happens for one agent in the self-consistent field created by all the other agents. If each one has a different strategy, then you need to use this sophisticated method. So this was very interesting. I always mention that because I found that it's interesting to remember that spin glass are totally useless. In spite of the tens and hundreds of thousands of works on spin glasses, there was never, as far as I know, never an application of spin glasses that was even invented, and there is a lot of pressure from grant applications that you should invent, that it will be useful or something. Nobody really succeeded. Nevertheless, it triggered an incredible intellectual interest and developed a whole branch of physics which started to have expansions and ramifications in all branches of science. It was very, very, very nice. So it has been called a cornucopia by Phil Anderson, actually, in a series of very nice papers that he wrote. So this is a little bit of the cornucopia of spin glasses. I will not even try to read it because it would take the whole talk in order to do that. But just to say that it applies, that it has connections in very different branches of science, going from biology to mathematics, to physics of a disordered system, optimization, information theory, a lot of things with information theory. But I want to tell you specifically about one connection, which is the connection to machine learning and large dimensional infinity. So machine learning is witnessing a technological revolution. This technological revolution, the date is very clear. It goes back to 2012. There was a lot of things of machine learning that existed before. I worked on what was called at that time neural networks in the 90s. There were a lot of concepts who were present at that moment. But there was then there was one of the many winters of artificial intelligence after that. And at some point in 2012, there appeared something that using some sets of networks that I will explain later on, it was possible for the first time to analyze images. That is, I give you an image, and the program is able to analyze it completely, to segment it, to tell you, well, in this image, it is a conference hall, there are this number of persons, they are watching, there are 3 of them who are sleeping, the few of them are awake, etc., etc. All these things. And that was the first time that it was doing it better than any other program. And since then, there has been incredible progress. Every 2 or 3 years, there is a new kind of technological revolution. And in images, in language analysis, now in image generation and language generation, I will come back to it. In science, the possibility of finding protein folding, finding the shape in which a protein is folded, starting from the sequence, was a major problem on which we physicists, chemists, etc., have been working a lot, with all kind of very clever dynamical simulations, etc., etc. In the end, it was solved, of course, being based on all the previous work, because that's the smart part of artificial intelligence, that it will use a lot of the database that has been generated in the past, but then it finds new structure from a purely statistical point of view, without needing to go back to the physics or the chemistry. And there is also playing games, chess, Go, poker, video games, etc. So that is a very impressive moment. And I will argue that this technological revolution presently is waiting for a general theoretical framework. So what is the tool? The main tool is really what is now called deep neural networks. So neural networks are systems in which the information is encoded in what is called artificial neurons. An artificial neuron will be a variable which takes a real value. It could be a 0, 1 value, but let's take it real, let's say. And so you have, for each circle like that, you have a variable. And then what a variable does is it receives signals from the previous layer, and then it does a linear superposition of the signal with some weight. So the neuron number I, there will be a field arriving from the previous layer, which is sum of wij xj, where xj are in the previous layer. And then it applies a nonlinear function. Okay? And that is sent to the next layer. Very simple. I mean, you don't need to have it's not something fancy. It's just mostly linear algebra with threshold. Nothing more than that. Well, and that is a machine. In a machine, what it means, it's a machine that if I give it an input, the input could be an image, it will give me an output. And the whole problem will be to train this machine. This machine depends on a lot of parameters, and the parameters are these weights that they are called synaptic weights. So it tells me this neuron, it depends on the weight which is here, the weight that are, etc. How it modulates the input from all previous neurons. Each time you have a new set of weights, you have a new machine. The number of possible machines is enormous. And it is known that these machines, if they are deep enough and broad enough, they are able to be universal computers. So the problem will be just, and this is the thing that is really new, the idea, new. I mean, it goes back again to a few decades. But the idea of machine learning is just that generating this way so that the machine achieves the task that you desire. So the task that you desire would be, I give it an image and it tells me if there is a cat in this image or not. That has been one of the main problems that people have been able to solve. Okay? Not the most important scientifically, but it has been a very big benchmark. And there are good reasons for that. I will come back to it. And so it was not possible to do that by hand, really. That is, in computer science, you would like to program the thing. Maybe you say, well, I will look if there are some small triangles, that would be the ears of the cat, and then if they are related to these triangles, I will look to some straight lines, that would be the mustache of the cat, etc. And then there is a cat. This never worked very well. The thing that works was telling the machine how to train itself. And so what has been done is the following. So each machine, the machine implements a map. The Xi is the input. It's an image in n dimension. Y is the output. And maybe it could be just 0, 1. There is a cat or there is no cat, for instance. And Y is a function of all the weights and the input. Okay? And what I have a database. And that is the thing which is crucial. I will assume that I have a large database of examples of input-output. It means that I have a large number of images in which I know if there is a cat or if there is not. And that is where the modern time comes in, because of the web and the possibility to put pictures on the web, what everybody did, not me, but many people, they put pictures of their cats. And so all of a sudden, there was available an enormous database of pictures in which we know that there is a cat. That helped a lot. And so you have this database, and so the psi mu will be the input number mu, and y mu will be the desired labor, and that is supervised learning. And what you do is that you define learning as an optimization problem. That is what you want. You would like that the machine itself, through some training dynamics, will find the set of weights that minimizes the training error. And the training error will be just the error. If I give you the machine, I give it the input, it gives me the output corresponding to that. I compare it to the desired output. I measure the difference, square difference, for instance, or other function, never mind. And I want to optimize that. And if I am smart enough, I am maybe able to push this error to nearly zero, which means that my machine will have found a set of weights which perform very well on the database. On each image of the database, the machine will tell me cat or not cat. Okay? So this is done. So this a priori, it's a good idea, except that it is doing an optimization in an extremely large dimensional space. You have to know that I did not mention the order of magnitude, but you have nowadays systems in which you have hundreds of millions of neurons, you have hundreds of layers, and you have the number of weights, which can be 10 billions. So we are looking at large-scale systems. How people optimize this thing? Well, they tell the machine to do it by gradient descent. The most simplest thing, the first thing that comes to mind, take the gradient of this function and you move the W in the direction that diminishes the energy. Stochastic gradient descent, it's a small variation on it, very crucial in practice, but I will not. But that is how it is being done. Still takes a lot of operation. Just one order of magnitude that is worth remembering. If you look at ChatGPT, it contains tens of billions of parameters. I don't remember by heart, but something like that. But what I remember is that the number of operations that was done for optimizing this function, the number of total floating point operation doing the gradients, etc., it's an easy number to remember. It's 10 to the 24. Okay? Avogadro number. So you understand it was a budget to do it, certainly, and a lot of being clever also. So the big challenge is, well, the first big challenge is to be able to minimize this function, hopefully getting it close to zero. The second big challenge is it possible to generalize? That is, once you have found this W, you present a new image that it has not been trained on. Will it be able to decide if there is a cat or not? And that is the big challenge. Just to mention, I don't want to go into technicalities, but basically the problem of learning, it is the problem of finding a set of W's in a very large dimensional space. You can have some prior, for instance, you would like that the weights they should not be too large or too small. Maintain the system in a range in which it works well, so you could put a Gaussian prior. And you put e to the minus beta times the energy, and the energy is the number of errors. This turns it into a problem of statistical mechanics. My variables are the weights. There are many of them, but this is my home. I am a statistical physicist. Handling many variables is something that I should know how to do. But the interaction between the variables now, they depend on these random parameters, which is the images and the desired label. This plays the role of the quench disorder. This plays exactly the roles of the position of the impurities in my spin band. So it means that for each new database, I have a statistical physics problem. I have to optimize the weights that will fit the database. And so, of course, if I want to do theory of that, the thing that I will need to do is go to an ensemble of databases, which will allow me to take this first step that I was mentioning before. So there are really two ways of handling this problem. Either you look at it numerically for a given database. That's the large majority of the work that we do. But if you want to do theory, the nice thing to do is to be able to control what happens in the database and be able to generate a statistical ensemble of data. And that is the field of what is called generative model in machine learning. So what is what is the novelty? The old ingredients, feed-forward neural networks, have existed for decades and decades. And as I told you, at the end of the 90s, they were, apart from a few people who were smart enough to stay in the field, most of us went to other fields because it did not really deliver. There were nice physics which is being done with that. But it did not work as a tool, it did not work as an application, it did not solve any problem. And they were already trained with gradient descent learning, implemented with backpropagation. All the main ingredients were there. What has been new since then? The availability of very large databases, image of the cat, much larger computing power, crucial. The main reason probably of the winter and why it came back now. Availability of very efficient libraries, high-level libraries, which allow you to program these things very efficiently. Much deeper networks. This is related to the availability of computing power and large database, and a lot of tricks that I will not try to enumerate. So, surprises and questions. The first surprise is that training works. Training means finding the machine learning, finding the weights that are able to do a very good performance on a given database. How you find that? It seems a priori that it should not be possible. You are working in extremely large dimensional space, in an energy landscape which is disordered. With all the tiny details of this, it depends on the set of images that you have in the database. I mean, it's a mess. Still, it works. So it just means one thing. It means that experimentally, this is excluded. We are not in this kind of situation. We do not have a shaky energy landscape like we have in space. It's a simpler problem than the space. And that is very interesting in itself. Why do I say that? Well, because the use of simple stochastic gradient descent it shows you that it will find a set of weights that are zero energy, which means that it fits well the database, nearly starting, not too far from any initial point. So you are in this large dimensional space, you start from a random set of W, you do gradient descent, and well, it will hesitate a bit, etc. But then after some time, you find a solution which is not that far from where you started. So it means that the landscape is a bit simpler than expected. The second surprise is generalization. In principle, what happens is the following. If you look at the energy of training, this is this curve. The more powerful is your network, the more weights you have, the more deep you have it, the broader you have it, the more parameters you have to fit the data, and the energy of training decreases. And that's normal. In principle, in statistics, when you have too many parameters, the generalization curve, it starts to decrease, but then at some point it increases again because you are overfitting. Think about it. We teach to our students, we say, don't do a fit with 5 parameters. You get nonsense. You can fit an elephant. Here we are fitting data with hundreds of millions of parameters. Really? Yes. And the surprise is that instead of overfitting, maybe there will be a slight bump at some point, mostly on a kind of linear problem, but then it continues to generalize better. That is a very interesting second challenge. The third that I like also is really a nice theoretical problem. That is a sketch of one network. I don't remember what it is, but each box tells you basically that's for analyzing images. It tells you where the image is going. There are the various colors. There are the various functions, max pooling, etc., etc. Describes to you in a very high-level way the set of parameters that are in the. If I have trained it, I know. So all these, so you see that here There is one neuron, it will receive a signal from those, etc., and I know the weight. So if I have trained it, I will know maybe 10 billion weights. I know each of them. So I call this the dream of the neuroscience. That is, it's like you have the brain, you know what it is doing. It is looking at an image and telling you there is a cat or not. And not only that, but you can know the activity of each neuron and the synapse between a neuron and another one. What else can you hope for? So you have everything, you know everything, and you understand nearly nothing. Because the problem is that the final decision, it's made in various hierarchical levels of decisions, and you do not have a clear explanation of each level of decision. You don't know how they articulate it to each other. You know the result, you know that you put an input and you get this result. But the explainability is still missing. And that is that's a problem for the theorists, that's a problem for us, certainly, but it's also a problem for practitioners. I mean, if you want to use it as an autonomous decision-making device, well, we don't like to have a device that is a black box and that tells us this is what should be done. Okay? So that's why many applications, in my opinion, most of the applications that are really successful now, they are proposing something. They will propose to the medical doctor, oh, considering the input that you gave me, there is a probability 75% that it is this kind of variety of this disease and that it could be cured by this time. But the medical doctor will read it and make the decision. Because you don't want to rely on something which is probabilistic, drawn from a very large dimensional space in which you have no control, and not able to explain to you the decision. So it's not only it's a problem for the theorists, but also a problem for the practitioners. Let me skip the old example of statistical physics. The ingredient of deep networks. Three categories of ingredients: the architecture, how many layers you use, what the units are doing in each layer, what are the nonlinear functions, etc., etc. This is an art. Basically, you give me a new problem, I will start from a network that has been doing well on related problems. For instance, if the problem deals with images, certainly starting from a network that has been trained to identify images, even if they have nothing to do. If you want to identify a melanoma and you want to see a skin lesion and decide what is the probability that it is cancerous or not, important application, and really practical one that is very useful, very successful, by the way. It's better to train your network not starting from zero, but starting from a network that is able to recognize images, able to recognize a street or a conference hall or a cat and a dog, because it already has a lot of the local descriptors that starts to analyze the image. And then you will adapt it, and you will not need billions of images of skin lesions, but you will adapt your previous network to the new situation. Learning algorithm, it's also an art. The nearly most naive algorithm, stochastic gradient descent, initialized with small weight, seems to work. Wonderful, but why? And then there is a last ingredient, which I want to insist upon in the last 10 minutes, which is data structure. And this is, I think, one point that we theorists, we have really underestimated in the previous decades. And maybe the tasks that machine learning addresses successfully are easier than expected, because the data that they are processing and that they are using for training has much more structure than what was assumed in theory. And usually old theories were doing two things. There were some kind of probabilistic mathematical theories that will tell you what happens to a machine in the worst case. So they will tell you what is the error that you do if you train the machine for this number of time steps with this size of database, and you have a kind of error function that decreases with the size of the database, and you can have a worst case analysis. Very nice theory, sophisticated, very far from the reality, because it's worst case. And then there were the statistical physicists. The statistical physicists, they come with ensemble. They tell you, oh, you like to work with one given database, but I tell you, the best thing, if you want to do theory, is to have a generator of database. So you have an ensemble. And then we do ensemble. But ensembles are hard to deal with. So what we were doing is ensemble of images which are IID pixels, black and white, probability 1/2. Look at a 1000 by 1000 image with pixels which are black or white with probability 1/2. It does not look like a cat at all. You lose all the local structure, you lose a lot of things. And so this is a chapter in itself, and that is what I want to address. The data structure is, they combine several interesting properties. Data, in practice, it has a combinatorial nature. It's made of pieces which are combined together. It has a hierarchical structure on many scales. It has a semantic structure, and it lives in a low-dimensional manner. There are 4 structural properties. I want to illustrate them very rapidly. So combinatorial is a picture of a conference hall. You see that it is combinatorial. I mean, you have a certain number of characters. Each character has a head, arms. The head, generally they have 2 eyes. Half of them has glasses, etc., etc. At each scale, so you have this combination. It's a hierarchical combination, and it's combinatorial in nature. If I want to draw one person, I have to decide what is the face, what is the eyebrows, what is the nose, what is the hair, and glasses or not glasses. And that will give me one character. Now, nice paper that actually was influential in the development of a large language model. If you take a database and you take the empirical correlation, which is the correlation of the activity of at 1 pixel and activity of pixel i and at pixel j, then you find a correlation matrix, and you look at its eigenvalue distribution, and you find that in a lot of the practical database of images, you have a power law distribution of the eigenvalues of this random matrix. Approximately, but then it depends how you sample, but it becomes better and better if you go to large database. So it's very, very different from what you would get for IID distribution. Here there are experts on random matrix theory. In random matrix theory, you would have, if they would be IID, that would be a Wishart matrix with a Marchenko-Pastur spectrum. It does not have the power of spectrum. It's very different. Semantic. So if you have, this is a large language model. Large language models, they are like ChatGPT, etc., etc. They are trained on something slightly different. They are trained on guessing the next word. So you have a text. I took a text on the web, and then at some point there is I interrupt the text, and I ask you to guess what is the next word. The private jet carrying Prigozhin and his entourage crashed late on Wednesday afternoon in the region northwest of Moscow, immediately raising suspicion of, and you have to guess the next one. Okay. That is something that has been studied for many years. Shannon himself in the 50s was working on that, trying to find that. And basically the first thing that you do is that you look at the statistics of, let's say, the 3 previous words. Okay. And you look in all the texts that you can find, what are the triplets, how many times you have seen suspicions of and what was the frequency of the next word. And from that you find the most probable and you give it the result. So this, if you take just 3 words, it will not give you a very good result. You would need to go further, but if you want to take even 12 words, you do not have enough statistics because the combination of 12 words, there are many of them. So you lost statistics. And maybe a key to understanding what would be the next word, maybe the key was lying somewhere up there. Maybe Vladimir Putin was an important ingredient to guess what is the next. So this is something that has been really the success. In this case, it was an assassination, and the rest of the text. So the large language model, what they give to you is what is the most probable next word corresponding. And they have a device to do that, which is called the attention mechanism. The attention mechanism is something that the system is trained upon. It is trained in trying to say, of course, the last few words are important. Suspicion of an, here you know that after an it has to be a noun, not a verb. It gives you a lot of, but what attention does, attention tells you far away, and far away can be thousands of words before. There are important words, and you should pay attention to them because they will have a good correlation with what happens here. And so this is a mechanism of attention. It's trained. It's again machine learned. I mean, you have to train the system in order to find the good attention mechanism that will help it to guess the next one. But one thing that I want really people to remember is that what large language models are trained on is finding just a sequence of most probable words. They have no representation. They don't know what they are talking about. There is no reality behind that. It does not mean anything. Assassination means nothing for a large language. Just one word. It happened that it was the most probable word. So they generate text by this thing here. So one should not attribute an intention to the ChatGPT when it does something. It just tells you sequence of most probable words. Here. And maybe one last thing that I want to say, here very rapidly. Among the many databases that there is a database of handwritten digits called MNIST, and they are standardized. Each digit is 28 by 28 pixels, 700. So it lives in a 784-dimensional space. Okay, but if you take a 28 by 28 black and white system, it's in general it does not look like a handwritten digit. One thing that you can look at is what is the intrinsic dimension of digits. There is a nice tool to do that, which I think was first invented by Grasberger and Procaccia for dealing with the dimension of strange attractors in dynamical systems. And the idea is to say, let me assume that I have a database of size p in a d dimension, and my points are in d dimension. Then each point occupies a typical volume, which is r to the d. So the typical distance from a point to the nearest neighbor will scale like p to the -1 over d. So if I can sample my database with, first of all, I take p relatively small, and then I add more points, etc., etc. I look at how this scales, it will give me an effective dimension. And when you do that for handwritten digits, you find nice power law scalings. And these power law scalings tell you handwritten digits, they do not live in 784 dimensions. They live in a subdimensional, in a manifold of dimension more or less 15. It's not a linear manifold. That would be too easy. It's a crumpled manifold. A manifold that is hard to find. But then you can do it for every digit, and you find a dimension which for the digit 1 is about 7 or 8, for 2 it is 12 or 13, for 5 it is 12, for 6 it is 11, etc., etc. So basically the MNIST problem is, in the 15-dimensional manifold of handwritten digits, identify the 10 perceptual submanifolds associated with each digit, and they are of dimension between 7 and 13. Not very easy, but it's much easier than working in the 784 dimension. And data is structured like that. So I have no time to, I was thinking that I would not have time to tell you about generative dimension, but the generative diffusion. I will tell you just one very, very short thing about generative diffusion. It's really one very hot topic at the moment. Generative diffusion is beautiful. It's really one novelty. This is something that was not done in the 90s in machine learning. The novelty of generative diffusion is the idea of generating new images you train a system from a database of images, for instance, images of conference halls, and you ask it, can you generate for me a new image that you have not seen? Okay? So you have a complicated probability distribution, which is a distribution of conference halls. You have examples from that. They live in very large dimensions. You have examples of that, and you want to generate new ones. So how you do that? You do that by a very, very physical process. You do that by a process of noising and denoising. You take each image in the database and you gradually add noise. And then at some point you get pure noise. And then gradually you will denoise by using a denoising algorithm that will give you back an original image, which hopefully will be in the same category. It will be also a dog, but not the same one as the one that you have. This is the idea. There are a lot of possible generative models. One of them is that I like because it's easier to explain to an audience of physicists, is is just using a Langevin equation. That is, you take a signal x. At time 0, it is starting from A. A is one of the images that you had. It lives in n-dimensional space. And you start from A, and you add noise. That is, you do a Langevin process. And precisely, you do it in an Ornstein-Uhlenbeck well. So it's a relaxation with a force that relaxes towards 0. And it will transform the data at large time. So it's just really the textbook example of the Langevin relaxation in a potential which is a quadratic potential. That's minus gradient of v of x is x. So it's a relaxation in a quadratic potential. So at large time, this relaxation will take you to an equilibrium which is just a Gaussian distribution. That's easy. Now the thing that happens is that at time t, what you have is that you have the convolution of the initial data, that is a distribution of my original images, with a Gaussian kernel. That is just what Ornstein-Uhlenbeck does. But now what you do is that you are able to go backward in time. And so you start from pure noise, pure Gaussian noise, and you go backward. And there is an exact equation that takes you back to the initial data if you know something which is called the score, which is a gradient of the log of the probability to be at time, to be at x at time. If you know that, you can construct this reverse Langevin equation, and it will take you back to the original distribution. And so what people do is they use this very physical system they use this very physical system, and what they do is that this core function, which is hard to know, they train it from data. They learn it from data. And they use a deep network that is able to, if you have a lot of data, you can approximate the gradient of log pt, and then they use it as a force field to get back to get an image back when you do the backward diffusion. That is how DALI, Midjourney, etc. are working. They are working on this very physical basic of system. They are working on random walk with Ornstein-Uhlenbeck. And so there are many questions, theoretical questions around that. In particular, what happens if you have phase transition, how the system is able to reconstruct several phases, which would mean several families of handwritten digits, or several families of cats and dogs, etc. I have not really time to do that. I will just keep to my conclusion slide. I have very interesting studies on that at the moment. But just to conclude, because I don't want to be late, machine learning needs a general theory. One knows everything but understands little. There is this property of emergence, what happened at large scale. And even if you know everything that happens on all the details microscopic scale, what is happening? Statistical physics can contribute to this theory, but it faces a new challenge, and the challenge is data structure. Data structure, it manifests itself in several aspects. The fact that the input is generally in a low-dimensional manifold. There is a combinatorial structure. You remember the various pieces of the image that are combined together. There is a semantic aspect, which are long-range correlation that they have to take into account, the attention mechanism, invariance of tasks with respect to some transformations. And in this respect, there is some common denominator all that, which is generative models, which are really a new development, a recent developments of machine learning, which brings a lot of very interesting questions. First of all, it is really able to generate new data, starting from a database. It generates to you a new cat that you have never seen. So understanding how the generative model works is a way also, it's interesting in itself because it's a big theoretical, big technological progress. but it's also a very interesting step for the theorist, which is how, if you understand that well, then it means that you understand well the structure of data. And you have a very good generator, you have a very good ensemble, and then I can start to do theory. So that is more or less the program. I started from 150 years ago and arrived at what happened last year. Thank you very much for your attention.
So thank you very much for this very interesting talk. I think we have time for questions. Yeah, questions from the audience. So just go ahead. I think you need a microphone. For the YouTube thing.
So there is a discussion about the ethical implications of several things involved in machine learning. Can you comment on that?
Well, in less than 2 hours, it's hard. But yes, I think of course there is, and there should be, and it's a very important question. In particular, I mean, there are so many aspects that I don't know where to start, but if I focus on a second on the last part of what I've been talking about, which is generation of new data, it's generation of new fake data. So it depends completely how it is being used. If it is being used in generating new protein sequences, which are good candidates for folding in such a way that they will interact with that anti-gene and that they will be a cure for something, wonderful. That's really a dream. And actually, there are quite a lot of companies which are now working on that. It's really revolutionizing the way of inventing new medicine, which so far was mainly done by Cribble. And now you can start to test your things also in silico before doing the. So it can be very good. At the same time, if you use it to invent a fake speech of someone with his voice and et cetera, that's a very big problem. So how to handle that is, I think it's a problem of ethics, it's a problem of the society. What is the right level of regulation? It has to be regulated. It has to be severely banned, the bad applications. I think it's a crucial problem because I don't know how to really manage a democracy if there is factories of fake news which are so easy to use. In fact, in my opinion, what we see is a drift in which most of us, we start to rely on information that we trust, maybe from some newspaper or TV or whatever that we trust. But then it happens that two different groups of people, they start to have completely different realities because they have different journals and sources of information that they trust. Maybe some of these sources of information are completely fake, you see that. But there are still a very sizable chunk of the population who believes in that. And so if we are not able to sort what is the reality, what is the truth, it's a very big problem. There might be some technological answers to that, which is the use of watermarking. Watermarking is probably a possibility, for instance, for images, how to be sure that, but again, it will be very difficult to implement. But watermarking the images that have been generated by an AI with respect to different watermarks for images that have been generated from standard camera. Of course, this is a very interesting subject of research in itself. The implementation of that will be extremely complicated because you have to realize that even if it is long to train a large language model and it takes time and money, etc., it's not that hard. And if you start from one which has already been generated and is made public, and there are several of them around, then you can adapt it to several tasks, and this is not such a big thing. So there is no way that you can imagine banning AI development. So one has to find the right ways of adapting, controlling, etc. And the main message that I have on this ethical thing is that I think that the main challenge is acceleration. I once gave a lecture to a public lecture, let's say, not scientific. And I said to the people attending, I want you to remember the two letters, A and I. A for acceleration and I for ignorance. And acceleration, I think, is the main theme because it's going so fast that each second, third year, there is something new that even the best practitioners, they did not think it would be possible. And even the regulators, they lag behind. You want to pass a regulations. EU did it. Actually, it did it rather well, but at the last moment, they had to add a whole chapter on large language model, which is the main issue now that they did not have because they had been working for 2 years, and that was not an issue when they started. So the acceleration is a big thing. Sorry, it's the shortest I could do for such a big question.
I was very intrigued about this process you described of generating new pictures from anyone. So you start from something which is known, then you add noise, and then in a way you have this inverse problem, right? You have to come back to more or less the same shape. Do you have to assume any specific characteristics on the data, like sparsity, say, or what's the main assumption of this?
No, there is no assumption. I mean, there is a theorem, and it's very general, but then it is a trick also in some sense, because what happens is that you might wonder, how is it that, okay, I start from a P0 of X, that's my initial probability distribution, I add a lot of noise, I run my Langevin equation, I go to something which is just uniform, Gaussian pure noise, and I'm able to go back. But how am I able to go back? I am able to go back by using the reverse Langevin equation, okay, which has a force, which has a shape which is like that. So this is just the Ornstein-Uhlenbeck guy. This is the noise, and this is the driving force. This is, dy dt, it has a force field. And what I'm using is a force field. What everybody is using is a force field. And this force field, it is something that ideally, it should be the gradient of the log of the initial probability at time t. Time t, I have a certain probability t of x, which is the probability of the degraded image. If I know that, I use that as a force field. But you know that when I go further and further closer to the initial point in my backward process, my pt of x gets closer and closer to the p0 of x, and this gradient will drive me to the initial one. So it's a tautology. It's a tautology. This also means that if I start from a database of image, and I have a perfect score, I will get back to one of the image of the database. Okay? I will learn nothing. So let me finish the sentence because it's important. So the whole trick is that you will use the gradient log p, which is not the exact one. It would be the exact one, the perfect one. You would regenerate the image that you already know. That's not what you want to do. You want to find a gradient of log p, which is a kind of smooth approximation of the true one. And this is smooth. This is one obtained by a deep network, and that is the one that you train. So it is still a very complicated function, which depends on a lot of parameters, which are the weight of this deep network, etc. But it's not perfect. And this imperfection results in some interpolation properties. It results in the possibility of generating new images which look like the initial one, but are not the same. This is totally uncontrolled. And in fact, one of the things, I did not have time to explain that, one of the things that we have been working on recently is how we can control this process, how we can understand when there is, the process that I was saying is when you get back to the original image, it's called the data collapse, the collapse on the data. something that you don't want. And so the big challenge is to understand how you avoid that. In practice, people, they know how to avoid that. They will train a large deep network in order to try to approximate the score. They run it, and if they find some image that is already in the database, they say, oh, it was too good, so I will train it a bit less, or I will reduce a little bit its size. Purely empirical. We start, in some cases, we start to have models of statistical physics in which we understand much better how this is done. That's the big story. Sorry, you wanted to.
Actually, my question was going to be about that. Yeah.
Okay.
More questions?
I have a related question to this generative models. You mentioned this example that you can train it with a lot of pictures, let's say, of the audience here of a conference. Then we can try to generate new photos of a conference audience doing this way of noise and going back. Can we expect from this way something new? So let me give an example. We train it with hundreds, thousands of photos of conference, and they will typically look like what we see now here. Can we expect, let's say, a photo of an audience where someone is wearing a ridiculous large red hat? Because in every example figures, there will be maybe no one wearing a large red hat. But it could be possible that someone comes in the audience wearing a large red hat.
Yes.
This is just an example. My question is related to this application of protein folding, which you mentioned, that we can, we try to use these methods to find something new. And my question is, are we able really to find something new, or are we just doing interpolations of what we had before?
Very nice question. The question which has to do with the difference between interpolation and extrapolation, to know if it's possible to extrapolate. First of all, if you go to your favorite generator of images and you ask it a conference hall with one guy wearing a big red hat, I'm sure it will give it to you. I'm sure. I did not try. I'm not an expert on that. But I go there this afternoon, I'm sure you will find it. How it finds it, so there is a whole gymnastics, a whole thing that I did not explain, also because I'm not expert of that, which is the interaction with the prompt. I mean, how you condition. There is a way of conditioning the thing so that it interacts with a certain prompt, like the story of the big red hat. And this is something which is a bit different. And so it means that it will have to rely on other bases of images in which the notion of big red hat means something. Okay, so it will combine them. But I'm pretty sure that it is doable. The question of interpolation versus extrapolation is a very important one. If you are in a very large dimensional space, even interpolation is already a mystery. In principle, you would need, it's very simple. You want to sample 10 points in each direction. On a cube, it's 10 by 10 by 10. You have already 1,000 points. If you are in dimension 1,000, it's 10 to the 1,000. And that's only for sampling. So this is called the curse of dimensionality. In principle, if you want to really have a good grid in large dimension, the number of points scales exponentially with the dimension. That's not what is happening. So it's clear that these systems are regularizing. They are not doing a good job even at interpolating. And they are also able to extrapolate. For instance, one recent data that I saw, which I found very interesting, is data of fully developed turbulence, in which you have, in fully developed turbulence, there is this phenomenon of intermittency, which means that you have rare events in which you have strong increments of the velocity. Caricature, but and then there is a power law distribution that tells you about that, and that's the multifractal exponents, etc. And when you do that, they are able to, they train the system with images of turbulence that have been generated by Navier-Stokes simulation, very heavy ones. They generate new ones. The new ones have the right tail. And because they can generate many new ones, because once you have trained it, you can generate many images, they can sample the tail even deeper than what has been in the generated system. This is new. This the nice paper very recently by Luca Biterale and his collaborators. We don't really understand how it works, but maybe, you know, in large dimension, it may be that extrapolation to some extent and interpolation, they are both very hard, and it's actually as surprising to be able to do one as the other.
More questions? So if not, so thank you very much.
Thank you.